Thank you so much for watching another episode of the Weaviate podcast. I'm super excited to welcome Tengyu Ma to the Weaviate podcast. Tengyu is the co-founder of Voyage AI and an assistant professor at Stanford University, which I think kind of already sets the stage of why this is so exciting, why we're so excited to be adding Voyage embeddings into Weaviate. We have a new text-to-vec Voyage module, and Tengyu has published so many amazing works in deep learning, contrastive learning, just so much. I'm so excited to be learning from Tengyu and welcome you to the podcast. Tengyu, thank you so much for joining.
Yeah, thanks so much for the introduction. Yeah, thanks so much for having me here. Yeah, this is a very energetic introduction. I wish I also have. Yeah, thanks so much.
Awesome. Well, awesome. So could we kick it off with kind of like what motivated you to start Voyage AI?
Yeah, so I think this is a very good question. So I think I started to think about this probably around early 2023. I think I've done a lot of research in Stanford. My team has done a lot of research on large language models, deep learning theory, so on and so forth. I thought that it's a good time for me to use my expertise in AI to contribute something to the commercialization of AI. And I thought that enterprise AI is one of the most important directions. So there are a lot of explored applications of AI in enterprises. We can revolutionize the industry in many sense. So, and the enterprise AI, I start to think about what's the best approach to use AI in enterprise. And at that point, I thought that RAG, we bet on RAG. We thought RAG is the right approach, and it turns out that I think we are kind of on the right track to some degree, because in the last year there was some debate, and then gradually it sounds like people are gradually converging to RAG over fine tuning in the last year. So, and I think in the early 2023, I think there was still a lot of debate, and now most people say at least RAG and fine tuning probably coexist, or maybe some people are just only using RAG. And in early 2023, I was thinking, okay, so how do you have a company, on RAG? There are many other startups doing RAG. In some sense, you connect different components. You connect the embedding models with vector store, with large language models, and you can do some good UI. You can have some domain expertise to understand the user requirements, so on and so forth. And there are many of these startups. And I was thinking to focus on the technical side because I do believe that the retrieval quality can be improved, the RAG overall quality can be improved. And then later I realized that maybe it's actually better to focus on component, because that allows you to be horizontal, right? So if you say, I'm going to have a RAG startup and my retrieval quality is much better than the other people, sometimes it's very hard for you to justify why the technical differences is important. So, and however, if you focus on components, you say, I'm only working on the retrieval system, and in particular, the quality of the retrieval system is responsible, depends on the embedding model, which we can discuss more. So then you can work on embedding models for many different areas, right? You can have finance, code, legal, so on and so forth. That's actually what we are doing right now. We have a sequence of domain-specific embedding models for every domain, and we can go horizontal, and we can work with many different people. We can work with RAG startups. We can work with enterprises who build RAG by themselves. We can work with the platform people who design platforms for serving RAG, so on and so forth. So that's how we maximize our strength, which is the research, the quality of the AI models, and in some sense, kind of like also go horizontal and maximize the market size.
Yeah, I love everything you're saying. There's so many in that, from the RAG versus fine-tuning debate nugget, the whole scope of RAG and all that kind of end-to-end system-specific component, horizontal business, all that. And so, yeah, and then the domain-specific thing is definitely a big topic we're going to dive in. We're super excited about the Voyage code models. I think a lot of Weaviate users are probably going to be really excited that we finally have a really strong code embedding model integrated with Weaviate. But I'd really love to dive into embedding models, contrastive learning. For me, my interest in vector representations came kind of during like the SimClear, MoCo, this kind of like self-supervised for computer vision. And I just think you'd be the perfect guest to kind of take us through like contrastive learning theory and all this kind of stuff.
Yeah, so I guess just a quick introduction to some of this contrastive learning and embedding model stuff. So embedding models, as many people know, are turning documents or images into vectors. So basically, you are training a model that outputs vectors. So you need a different loss functions. And the loss functions, as you suggested, are called contrastive loss. And this contrastive loss was first designed for images. So basically, people said that I need to learn visual representations, and how do I do that? I don't have any labels. Suppose I have a lot of images and I don't want to use labels. And then what people do is that you augment an image into a similar image, and then you say that this augmentation and the original image should have similar representations. So that's part of the loss function is trying to incentivize. And also you want to incentivize that a random pairs of image have different representations. And there's a sequence of loss functions, contrastive loss, sim clear, sim sam, spectral contrastive loss, so on and so forth. So these all are operating under the same principle. You want similar images to have similar representations, and similar images mostly is defined as augmentations of the same image. And then you also want random pairs of images to have different representations. And how you exactly design this loss function to incentivize these two principles can vary across different methods, and there are trade-offs, on various fronts. But generally, all the contrastive learning algorithms are like this. And now these days, people are using these contrastive learning algorithms for text as well. And the same thing, you want similar text to have similar representations, very obvious. And you want, random pairs of text to have a different representations. And then for text, it's even a little bit more complicated because you have to define similarity in the right way. So whether similarity just means that semantic similarity, or maybe similarity could also mean that you match the keyword. Similarity could also mean that there's some relationship, but not like exactly the same kind of semantic meanings. Sometimes it's question and answer pairs, so on and so forth. Yeah, so that's just generally what people do for learning text embeddings with contrastive loss.
Yeah, I think there's so many great kind of points in this story. I like the last point about what kind of relationship is captured by embeddings a lot, especially with code. I can imagine, like if I search with the query of a doc string to try to match a Python function instead of like another doc string, and then like in this kind of nuances, things like question to answer, and there's a lot of nuance there. But so kind of parsing this out, I think there's the tour of kind of like loss functions, triplet versus in batch, and data augmentation and semantic similarity, and kind of presenting representational collapse. There's all sorts of like topics in the air, I see. Could we maybe kick it off by, if we could, I think it may be really interesting to start off with data augmentation. So with images, I know you kind of have this like, the invariance to like rotations or horizontal flips. With text, I personally have a little background of this, of doing a survey on image data augmentation. And then I tried to like take my lessons to text data augmentation. I found it a little bit harder to preserve the label, to preserve the semantics of text data. But now I imagine maybe with generative models, you can transform positive pairs. What's been your experience so far with that kind of positive data augmentation supervision?
Yeah. So maybe just to set up the baseline in some sense. So the augmentations, as you said, is very important in this contrastive learning because you rely on this augmentation to create the so-called positive pair, the pairs of data you want similar representations. So and however, this is not, it's not like this decides everything, because for let's say for images, right? It's not true that in image world the only similar images pairs are just augmentations or rotations, flipped translation of each other, right? So there are also image pairs which are very related, and they are not translation flip like crop of each other. So but their similarity are still learned by this contrastive learning algorithm. And why? The beauty here is that even though you define the similarity in a very narrow way, you say only two images which are translation of each other are similar in your loss function. But when you learn the model, this similarity propagates. So basically, what happens is that in the image, this is actually related to some of the papers we wrote that explains why contrastive learning work. So the theory we had in the paper is that suppose you have, for example, two dogs. They are not translation or augmentation of each other, right? So like there are two huskies and there are two different huskies, maybe with even different color to some extent. why you can learn similarities by contrastive learning of these two huskies. And the reason is that even though they are not augmentations of each other directly, you can find a sequence of huskies that connects them. So basically, there is you can imagine like for any two huskies, you can find maybe a sequence of 10,000 huskies images, such that every consecutive pairs of images are augmentations of each other, and you gradually change one husky from the other husky by gradually moving the position, the posture, cropping, changing the color scheme, so on and so forth. So you can move from one husky to the other. Of course, let's say suppose there's 10,000 huskies that connect these two huskies together. It's not true that in your image data set, you have these 10,000 huskies, because you don't have such a big data set. But such images exist, but they don't necessarily exist in your data set. And that's the beauty of generalization. So basically, the claim is that implicitly, the contrastive learning algorithm actually learn how to work on a much larger family of population of images that includes all of these hypothetical images I was talking about. So, and then you learn. So basically, if you are given infinite data, then you should be able to learn all of this relationship. And now, why you actually also learn with finite data, and that's because the neural networks has some generalization capabilities, so that finite data is actually not very different from infinite data. And so basically, even though you don't see this whole sequence of huskies, in your training set, but implicitly you are learning the metric along this trajectory. So basically that's what I'm saying. What I'm trying to say is that even though the augmentations is only a very local definition of similarity, right? They are not all the possible similarity you need to know. You want to capture, but actually implicitly you can capture compositions of similarities by these contrastive laws. So that's why it's not, the algorithm are sensitive to the augmentation you choose, but it's not that you can only learn the similarity defined by the precise augmentations. You can still learn the compositions of similarities defined by the augmentations. Yeah, but now let's go back to your text example, right? So for text, it's a little bit more complicated to define similarities, because you can say a query and a question are similar. You can say a question and the answer are similar, right? So the answer to a question are form a similar pair. And you can also say two questions that asks about similar concept are similar. So and maybe there are other definitions of similarity. And what we do is that, and this is also, roughly speaking, also some of the other published papers have done, is that you just try to create a variety of different augmentations. And you just add, all possible kind of like augmentations or pairs of similarity that you can think of. And then you rely on the magic of neural networks to propagate or compose this similarity to even more complex definition of similarities that you don't know. So, and with these two, with your handcrafted definition of augmentations, and also with the beauty of neural networks compositionality or kind of like extrapolation power, then you can learn a variety of possible similarities in the embeddings.
Amazing. I love that kind of like local broad generalization. I really like that Francois Chalet had on the measure of intelligence, and that really helped me think about it for people maybe listening who are curious about this kind of thinking about these points and visualizing it. So I guess so I really like this thing of like, positives could be paraphrases of text, or maybe it's semantically similar because this is an answer to that question, or whatever other kind of like relationship like that you can imagine. And it just really inspires me to ask you this question. I've asked this question to Nils Reimers at Cohere, as well as Zach Nussbaum at Nomic, of like, what's your experience with creating the data set that's used to train these embedding models?
Yeah, so we have I first of all, I don't know everything about how people create data sets in my team these days. And second, I probably cannot tell you everything either. So, but I think what I can say is that there are a lot of trials and errors, and a lot of like human intuitions in the definition of the positive pairs in preparing the data sets these days. In some sense, the way I think about this is that this is one component, the data set preparation or data set curation, if you think a little bit more broadly, seems to be one of those components in AI these days that require a lot of human intuition and human handcrafting manipulations in some sense. Like it's always like a reminiscent of the feature engineering 20 years ago or 10 years ago. Like 20 years ago, people always use linear models. There's no way you can change anything about the model, right? It's always linear, maybe sparse. And the only thing you do is you craft a feature, right? You define the feature yourself, or you define the kernel function, which is the same as defining the feature yourself. And that's the kind of innovation you do, but that's also kind of like a very ad hoc process. So you cannot really publish a paper saying, okay, I engineer my feature in this way, based on my data and based on my intuition, based on my understanding of this particular application, I engineer my feature, right? You cannot publish a paper like that. But that part is pretty important. So it's a little bit similar these days when you talk about data curation, right? Because it's kind of like the data curation is a pretty ad hoc process, at least so far. Actually, I have some papers that try to automate that, but so far, I think majority of people are trying to curate data with intuition and with handcrafting. So, but the beauty of the modern AI is that the users don't have to do that. So basically, the model provider, right? So before, the users engineer their features based on their data set. But now the model provider, like we train the model for you, we do all of this engineering stuff, or like data curation stuff, for the users, and then as the end users, you can just use this AI model as a black box. I think that's the difference. But in terms of but in terms of the technical, low-level technical details, it sounds like reminiscent of the feature engineering to me these days.
Fascinating. I mean, I've been super interested in like the DSPy synthetic data framework, and I guess so. Maybe one experiment we did at Weaviate, Erica Cardenas had she generated synthetic queries, and then we used Cohere's fine tuning for their re-rankers, and we were kind of studying this idea of how do you connect the loop between the query, like how you generate the queries, and then you have this fine tuning with gradients in this loop. And so with the feature engineering, I'm almost thinking like this the prior on like the prompt of how you would generate like a positive example from this point, that's like the features, and you curate a set of those kind of prompts, and that's how you have this like automated engine. Is that kind of?
Yeah,
And
so that's when that's what I would mean if I use synthetic data generation. So although most of our training, like we have a complex pipeline these days. We have multiple stages of training. So but most of our training are not using synthetic data. And the reason is the following. So generating synthetic data is also expensive. like so, and we are training on trillions of tokens, and if you just generate synthetic data with trillions of tokens, it's actually pretty expensive as well. It's expensive. Sometimes it's expensive as training those tokens. So, and also the synthetic data, still there is in limited diversity in the synthetic data. So as you said, you can tune the there are many ways to tune the prompt to make the synthetic data much more diverse and realistic, but still sometimes it's not as good as the real data. In some dimension they could be very good, in some dimension they may not be as good. So that's why we use a mixture of real data and synthetic data, and the real data is much bigger than the synthetic data. The synthetic data is higher quality in some dimension, in the sense that you can be very clear about what data you want. But the real data has more diversity. It covers all the noisy cases in the real world, and also it's much bigger and cheaper.
This kind of discussion of diversity, I think, will transition us perfectly. I think we did go pretty deep into the data set topic, but I think kind of diversity and maybe clustering the representation space. I'm very curious about this idea that one of the papers kind of around SimClear and MoCo time period was suave clustering, and I know you've done some work with like spectral clustering and setting that. What role? Like, I have to think that clustering has some role to play in learning vector embeddings when you're trying to maybe just enforce a prior on how to distribute the space and avoid representation collapse and all this kind of thing. What role maybe does clustering have in training embedding models?
Yeah, so I think there could be, so maybe let me just briefly talk about some of the papers I wrote, which is actually one of my favorite paper on understanding how some of this contrastive learning work. So this is called, this paper, analyze an algorithm called spectral contrastive laws, just mostly for that the spectral contrastive laws is easier to analyze. So, but they are very similar to sim-clear and other loss functions as well. But basically, the main idea is that whatever contrastive laws you are using is kind of doing the following. So basically, imagine that you have a manifold of images, right? For text, it's probably a manifold of text. Text is discrete, so it's a little bit different. But let's use images as an example. So you have a manifold of images, right? So or maybe a lot of manifolds, right? Maybe a manifold for huskies, a manifold for cats, a manifold for desks, a manifold for other landscape pictures, so on and so forth. So you have many manifolds of images, and of course you have some samples from these manifolds as your training set, which let's not discuss for the moment. So you have a lot of manifolds, and you can imagine that you can build a graph on this manifold by doing the following. So you say you take a discretization of the manifold. So every manifold, instead of it's a continuous manifold, you have a lot of points on it. And then you say, I connect nearby points and I build this graph, which is kind of like basically, I think it's called proximity graph. So basically you build a graph based on the distances, the local distances on the manifold. And then you can actually prove that the contrastive learning algorithm are basically doing some clustering algorithm on this graph you just defined. So basically, in some sense, this graph distance is the same as the distance on the manifold. If you have 2 points on the manifold, on the same manifold, they have smaller distances. If you have 2 points on different manifold, they have very, very big distances. And this graph, if you can cluster in the graph sense, then you can cluster in the semantic sense, because every cluster in the graph, actually corresponds to the same manifold, which corresponds to the same classes or same concept. So in that sense, many of these algorithms are doing clustering. The only thing is that you are implicitly clustering of a lot of points, because you are thinking in this high-dimensional non-parametric sense, where you have like an infinite number of like images on the manifold, so on and so forth. Yeah, so that's one connection to clustering. And nice thing about this is that once you have the representation, the embeddings, right? So you can prove that the embeddings, if you do clustering, the Euclidean clustering based on Euclidean distance in the embedding space, is the same as doing the clustering in the manifold sense. So basically you can prove that Euclidean distance actually has a very nice semantic clustering property. So that's one connection to the clustering. And once you have this, but of course, like when you have text, the theory becomes a little complicated, because for text, it's not like you have very clear, well-defined clusters in the textual space, right? For images, every class is a cluster, or maybe every subclass is a small fine-grained cluster. But for text, every paragraph of text is about a few different topics, right? So there are a lot of overlapping clusters between texts, right? And sometimes you don't even know what's the right granularity you should talk about clustering, right? So should you talk about clustering in terms of the topic level, or should you talk about clustering in terms of some a little bit lower fine-grained level? So it's a little bit more harder to understand for the text space.
I love that. It unlocks a lot of thinking. Is that maybe my first question? Maybe leaving the manifold thing alone, because that just breaks my brain trying to think about that. But maybe I would kind of want to start transitioning into like the code, like embeddings for code. I've heard, like with text and the example you just said, it resonated with me enormously. I've heard a lot of people say, like, I want ice cream, I don't want ice cream. How should these be embedded with each other? And Nils Reimers had taught me about multi-discourse, and then coming to Weaviate and seeing tons of examples of paragraphs that talk about more than one thing. So is code maybe like more naturally atomic, maybe, like, because you're going to kind of cut up a function, a part of a function. Maybe it's, easier to chunk up than natural text.
Yeah, so I think even for code, sometimes is I think interesting that they use the word multi-discourse. So so sometimes every piece of code has different dimensions you can cluster in some sense, right? So one dimension is the functionality of the code. And maybe another dimension, another aspect is the programming language used for the code. I mean, another aspect is that what's the surrounding context, right? So which code file this code block belongs to, and whether it's a helper function, whether it's the main function, right? So which layer it belongs to, so on and so forth. So I think it's probably still a multi-dimensional, multifaceted concept. So, and the idea is that the embedding model will capture all of this to some degree in some different coordinates, right, of the embeddings, or some different dimensions of these high dimensional objects. You don't exactly know where they are captured, but they are captured somewhere hidden in that high dimensional vector. And it's up to you to retrieve those in some way when you need it.
Listening to you talk about this, I'm now just inspired to ask, like, is L2 distance, where we try to kind of like just compare all the vectors to each other, do you think that's maybe not the best way of doing it? Like maybe you have like a PCA factoring of the dimensions of the vector, or you like, just kind of just my natural curiosity from hearing you explain this is thinking that maybe there's something more than L2 distance for comparing vector embeddings.
Yes, I think in the long run, it should be. But there are several different ways to deal with this. For example, one way you can deal with this is that you can add prompts in your text, right? You can prepend some prompts in your text, and if the embedding models are trained properly, then these prompts will kind of like automatically rotate or convert the embedding models in different way so that you can still use L2 distance. So basically, my vision is that I think L2 distance as a metric for embedding space should still exist and probably still exist for a long time. And the main reason is that that is really fast, right? That is really good when you do the search. So in some sense, that's your top one priority to insist. And then you do other things to accommodate for that, right? You can allow prompts to change your embedding to kind of attend to special dimensions of the embeddings. You can also train your embedding algorithm. You can fine tune the embedding algorithms to emphasize certain aspect of the similarity, right? So and you can probably do other things to disentangle certain aspects. You say maybe the first 500 dimensions about the functionality of the code, and the second 20 dimensions about the maybe the other kind of like aspects of the code, so on and so forth. So I think but you try to kind of like insist that at the end of the day use some L2 version, some L2 similarity, so that you can have faster search. So right now, I think the Voyage code embedding, we are mostly focusing on, during the training, we mostly focus on the functionality, right? So we want to make sure that the model understands what the code is really about, fundamentally, which algorithm is implementing. And we also focus a lot on the keywords. We focus a lot on basically everything that we can think of right now. So, but I can imagine in the future, someone has a particular uh, um, similarity they want to optimize for, and that's a perfect time to use either some prompt or using some fine tuning on top of the embedding models. And we are going to provide some fine tuning API soon for people to do that, and we can also fine tune for people right now. So I think these are probably the more I would say maybe this will exist for a long time. And like I would predict that this is the way we go forward. We insist on the Euclidean distance, but we change other parts.
Hmm. Yeah, again, that just inspires so much thinking. I like one thing with Weaviate 124, we started supporting multi-vectors, and Weaviate 124.2 will have Voyage AI plugging the Weaviate features.
Yeah.
But so, what do you think? Like, this idea of maybe having, like, I really like this paper, Prompt Bert. I'm not. I had kind of, this was maybe like 2 years ago, so it's not like fresh in my memory. But I'm not. I don't recall exactly what you would kind of put before text before you embed it. But maybe something like, I don't know, like this code belongs to this folder, and you kind of use the metadata to put it in there, and then you get the embedding like based on sort of where it's located in the code. So I really had wanted to ask you this question about, like, single vector, pooled vector representations in the index, or say maybe like a Colbert style approach where you re-rank with additional vectors, and maybe those vectors could be from kind of other sort of relationships, and it's not necessarily just like token vectors, as well as like maybe if we could throw this into the category as well of like matryoshka embeddings and sort of multi-vectors where they're like different levels of granularity. I hope that wasn't too much in one question, but
Yeah, so maybe I'll talk about each of them one by one. So I guess probably the first concept is about the Colbert, multi-vectors Colbert, right? So this is this technique where you don't only have one embedding model, one embeddings for a whole chunk of doc. You have actually multiple embeddings. Actually, in the original version, you have one embedding for each token, even, right? So, and because you have one embedding for each token, and if your trunk is like 512, maybe 1000, you don't have like 512 or 1000 embeddings for the whole for just a single trunk. And the benefit is that now you are more fine-grained because every embedding you have captures the very localized meaning of that particular position within the bigger context, right? So it's very good. It's very fine-tuned. The downside is that now you have to allow you have to store a lot of vectors, right? Before you have 1 million documents, you have 1 million vector, and now 1 million documents means 1 million times 1,000, 1 trillion vectors. So definitely a lot of burden on the vector database side, which is, it's great that Weaviate is supporting multi-vectors. That's great. But sometimes it could be too much, right? Depending on how you do the trade-off, right? It also depends on how many documents you have. If you have like 100 documents, probably doesn't matter. If you have 1 million documents, you have to think very hard, right? But that said, there's also middle ground. So one of my team member, Yujie, so he has published a paper on multi-vector embeddings, which is a little less extreme than Colbert. So Colbert has this one embedding for each token, right? So his version is that there are probably like something like you have a trunk of size 1000, and you have maybe 10, 100, or maybe 100 embeddings for this whole trunk. You don't do the all the way fine-grained level until you're on the token level. So that could be more likely, in my opinion, a good middle ground when you have a lot of documents, because you have a trade-off between quality and the space, right? And the vectors, the compute and space. So another dimension I would like to mention is that Colbert is about, or multi-vector retrieval is built on top of an existing base model, right? So Colbert is building on top of BERT. So even though the part col, the COL part, matters a lot, the BERT part also matters, right? So if you replace the BERT by Voyage, right, you definitely would get a big lift. And so that's why sometimes if you look at the benchmark, right now, so the Colbert, even V2, their published results are still not as good as OpenIDA. It's not as good as Voyage, so on and so forth, right? Even though OpenIDA, OpenAI V3, Voyage, all of these models have only a single vector. So basically, there are multiple different ways you can improve. You can make the model really, really good. You can also have multiple vectors. You could also have multiple dimensions of the vectors, which kind of like is about the other method we're going to talk about. So basically, there are many different ways to improve the embedding models. And right now at Voyage, we are focusing a lot on improving the core, the base, right? So that transformer, how do you make the parameters in that transformer as accurate as possible, as deep as can have as deep understanding as possible. But one day we may very likely also have a co-voyage, right, where you have multiple vectors version of Voyage. I think that's probably the future, where the future will go. But for now, I think if you just literally compare Colbert with Voyage, I think Voyage is still probably better than Colbert. But in the future, we probably have co-voyage, or maybe you call it something else, multi-vector voyage.
Yeah, super super compelling again. I guess maybe one more super kind of technical detail of embeddings and vector models before kind of coming into maybe code and the LangChain case study you did and things like building a product around an embeddings API. So kind of what you were just sort of hinting towards about new architectures for contrastive learning. I'm super interested in this. I think reading your paper on the inductive biases and contrastive learning, maybe there's something to like kind of latent bottlenecks and just sort of like how you design the dimensionality of intermediate layers of the transformers. And I think in what you're just saying, it already kind of was hinting to this, like how much more adapting of BERT is there to do for state of the art embedding models?
Yeah, so I think that's a great question. So in some sense, this is about how do we train the embedding models? How do we get it better, right? So it's a pretty complex process, as you can imagine. Because, for example, if you ask me, what's the secret source of OpenAI? I think these days the community probably would guess that there are multiple secret sources, small secret sources, all of them combined together and give the best model, OpenAI model, or maybe cloud, so on and so forth. So so that's kind of what's happening at Voyage as well, right? So we have already a relatively complex pipeline. We have some pre-training, we have some kind of contrastive learning, we have all kind of steps to deal with different aspects where we found that maybe the model is not as good um, as it should be on this kind of aspects. Then we have additional steps to kind of improve the capacity or the capability in that specific kind of like dimension. So and also you have so that means that for every step you have some data collection process, you have some data curation, you have to verify the quality of the data, and every step you have to tune the hyperparameters the best way so that they can tune fast. Because if you tune 3 times slower, it means $1 million versus $3 million. Oh, $10 million for $30 million. So that's why any efficiency improvement is very important. You have to choose the right loss function. You have to choose the right architecture, the activation function, the number of layers, the width, so on and so forth. So I think of course I don't know exactly what OpenAI or Anthropic is doing, but I think this is kind of similar to them in the sense that you need optimization for every component here, so that if altogether you get probably 10x efficiency improvement, maybe 100x efficiency improvement, so that you can train this model in a reasonable amount of time with the sufficient high quality. So yeah, that's pretty much what we do under the hood. We tune many of these hyperparameters, but I have to tell you that sometimes we don't tune all of them sufficiently well. The architectures, I think actually we are still taking relatively standard architectures. We tweak them a little bit, but not a lot. We tweak the optimizers a little bit, not a lot. We spend a lot of time on data curation. That's probably cost us a lot of energy. And we spend a lot of time on every different part of the system. So to get this embedding model done.
Yeah, I think that's sort of the consensus now, is that the data set curation is the most valuable thing, and you're pretty intense if I'm sure there are researchers at Stanford who do things like maybe that shampoo optimizer and the second order optimizers and things like that, and also the loss function, I think that triplet in batch and all that. But is neural architecture search, like, I think we just saw like flash attention, kind of like like there maybe is some opportunity there, but it sounds like using standard transformer architecture. Do you think neural architecture search is still promising, or?
Um, so we don't use neural architecture search in the sense that, I think it also depends a little bit on what exactly NAS you mean, right? But I don't think we use, at least not the most typical NAS at all. And we are still mostly using scaling laws and human to tune the hyperparameters or tune the architectures, right? So human means like you look at what's going on, whether the gradient is too big. You look at you use some kind of like analysis to guess which part of the system is a bottleneck, and then you fix them by tuning some of the hyperparameters, changing some of the activations, so on and so forth. And part of the reason here is that I think, I'm not, I've done some research on that along that line about NAS, but I think the NAS still requires a lot of compute if you really want to do it well. And sometimes it's hard to justify the use of the compute. Um, um, uh, uh, just, like the ROI is not good enough to some degree, right? Because if you use a small model to do the NAS, then sometimes the lesson you learn from the neural architectural search doesn't transfer to large model. But if you use a large model to do the NAS, then you spend too much compute. So it's very hard to strike a good balance there. So that's why we but we do a lot of scaling law, but right. So we try to like find out what's the best hyperparameter for the small model. We try to find what's the best hyperparameter for the middle model, and then we fit some curve, and we try to extrapolate that curve to say, oh, maybe this hyperparameter should scale linearly in the model size, and the other hyperparameters should stay constant as you change the model size, and some other hyperparameters should be inverse proportional to the number of layers, right? So you figure out all of this relationship, and then you scale up to the largest model and train once for a few weeks or maybe for a month, something like that.
Yeah, that kind of note on like, human hyperparameter tuning and graduate student descent, that kind of thinking. I think there's such an interesting new parallel there with like language models doing that kind of like observation. It's almost like Bayesian, but then it has this like prior in the language model, and I think that is definitely a can of worms we could open. But the scaling laws thing, I think scaling laws is just one of the most exciting stories in all of AI. And maybe really quickly before we graduate back into maybe higher level use case kind of stuff, if yeah, scaling laws and embedding models, like what's kind of the story?
Yeah, I think scaling law still holds a lot on the embedding models. Of course, I would say one caveat about the scaling law is that it's only an empirical observational law, right? In the sense that if you change something in your code, maybe your scaling law will be different. So, so we try to do that, right? Because sometimes you use a different algorithm, then the scaling law becomes much better, right? So, but still, I definitely agree with you that scaling law is the core of the modern AI, because you have a lot of predictability on a large model, right? You don't want just say run your experiments and just pray, right? You want to have some confidence on how good the experiments will be after 3 months. So yeah, so we do a lot of scaling law, and it's still true that for embedding models, the larger the model is, the better. So, however, for embedding models, the challenge is that you cannot make the model too big, because then the latency is not good enough, right? So this is supposed to be a very fast step. You can search some relevant documents in under probably at most 500 milliseconds, and in most cases probably 100 milliseconds, maybe sometimes 15 milliseconds. So, so you have to maintain the model to be small enough. And actually, we are using very small models to do this, right? So our model on MTab is kind of like 10x smaller than some of the other models with similar performance as us. And that means that you have to find a way so that your scaling law is better than others, right? Somehow your scaling law just shows that only 1 billion parameter model is enough, and other scaling law shows that 10 million parameters is enough to reach the same accuracy. So that's in some sense one of the key challenges we are addressing every day. How do you change the scaling law so that you can use smaller models to achieve the same performance, or maybe even better performance?
That's so fascinating. That's maybe one of the biggest misconceptions we sort of see at Weaviate is people who want to use like the biggest language model to embed their data set, and understanding that idea that you don't want to use like 100 billion parameter model to embed your document and all that. Awesome. So yeah, Tengyu, I thought that was just such an amazing overview of all these concepts. I can't wait to watch it back and just study it myself. Could we kind of transition into maybe a higher level thing? On the Voyage blog, you document doing a case study of searching through the LangChain documentation. So not maybe people, when they heard me previewing this, they thought I meant like a LangChain demo, but this is like the meta of the dog food of searching through the documentation through the LangChain code. Could you just kind of take us through that journey?
Yeah. So basically, what we did is that we fine tune the embedding models on LangChain documentation. And the reason we need to fine tune here is that, as you can imagine, the LangChain documentation are very new, right? They are only 1 year old, or maybe 1.5 years old, and there are a lot of jargon there, and also many of the concepts are also very new. You don't really expect that, an embedding model off the shelf understand all of those detailed logic about how to do RAG, right? And also those terminologies, right? So that's why fine tuning is almost necessary. And what we did, we started with our embedding model, a base embedding model, and we fine tune for the LangChain documentation, and we see 15% improvement in the recall. So it's something from 60% to 75%, which is great. So, and I think one lesson I learned, actually, there are two lessons I learned. One lesson I found is that it's indeed true that the retrieval quality highly correlate with the final response quality. Once you see 15% improvement in the retrieval quality, then the final response quality also improves a lot, because you get the right document, and then GPT-4 or maybe other language model can synthesize answer very well given the right document. And if they don't have the right document in context, they hallucinate a lot. They just guess what you should do with LangChain, but sometimes the guess is wrong, you know. So and the second lesson I learned there is that um, it's a kind of like a blessing of this particular setup, that such that you can fine tune actually on relatively small document set. So basically, when you say fine tuning, the first reaction you say is that, okay, if I don't have enough documents to fine tune, then I may overfit, right? That's actually somehow what's happening to some degree with the large language model fine tuning, right? If you don't have enough documents, sometimes either you overfit or you cannot override existing prior of the large language models. And if you have a lot of documents, then it works great. But you really need probably 1 million documents to fine tune large language models, something like that. Just at least people have found that it's difficult to fine tune large language models with a small set of documents. However, when you fine tune these embedding models, the blessing or the beauty here is the following. Let me give you a dream example. Suppose you only have 5 documents, right? Very small number of documents, 5 documents, and I'm going to fine tune an embedding model for you. And the most natural guess would be that I'm going to overfit to these 5 documents, right? And that's probably very likely true. My embedding model fine-tuning model will memorize your 5 documents just to death. So, however, that's not a problem. Why? Because anyway, you only have 5 documents to retrieve from. So the only thing you have to do is to retrieve from these 5 documents. You only have 4 confounders every time you have a query. Of course, when you have 5 documents, sometimes you cannot answer the query with these 5 documents, but there's nothing you can do anyways, right? And when you can answer, the only thing you have to do is to retrieve 1 out of 5. So basically, memorizing your 5 documents is not a big problem, right? As long as you only have 5 documents. The problem will be that you have I memorized 5 documents for you, but you have actually 1,000 documents or maybe 10,000 documents later. So basically what I'm saying is that if you the only thing you have to do is to fine tune the embedding model on whatever corpus you have for your retrieval. If your corpus is small, some memorization will happen, some overfitting will happen, but that's okay because anyway, your task is easy. You only have like 5 documents. Memorization is actually probably exactly the right thing to do for retrieval from these 5 documents. But if at some point you say you have 1 million documents now, and then what we do is we just do a continual fine tuning on this 1 million documents, because anyway, continual fine tuning doesn't take that much cost, because anyway, you have to embed or reindex this 1 million documents, right? So basically, you just take a path of training over this 1 million documents for training, and then you re-embed this 1 million documents when you have a bigger document set. And now you don't have this issue of overfitting, right? Because you already have 1 million documents, and the fine-tuning becomes really generalizing, and then everything is in the more normal situation of the machine learning, right? Everything is generalization, so on and so forth. Maybe sometimes you are in the middle regime where you only have 2,000 documents, then there is a mixture of overfitting and memorization and generalization. But anyway, you have 2,000 documents. That's probably the best thing to do for that 2,000 document retrieval problem. So basically, what I'm saying is that somehow, for some kind of, I'm still amazed by this this situation that for embedding model fine tuning, you can allow fine tuning for even a small set of documents.
Yeah, amazing. I guess it's just about kind of pushing the space apart, less so than the generalization kind of, and maybe it's related to like works on autoencoders compression, and it's not as much about generalization. Yeah, trying to
Exactly. When you have smaller number of documents, you are more about just how do you kind of auto encode this small number of documents. You don't necessarily have to generalize, just because the problem is easier.
Amazing. So then I'm so curious about how you opened it about like LangChain has new concepts even in the data set, and it makes me think that this kind of continual learning thing this is one of the debate topics that I'm always bringing up with people is this kind of idea of like zero shot versus continual fine tuning. I'm in the camp of zero shot. I think especially with Cohere's command R model, I like what I suspect they did to get it really good at RAG is they trained it with RAG and it was kind of maybe RLHF'd on like was it reliable to the retrieved context, and so I still kind of believe strongly that you can just sort of retrieve and then have models that are really specialized of grounding it in the context compared to this kind of continual fine tuning. But and then for embedding models, maybe there's something again to that prompt, Bert, where you kind of like retrieve, like a short paragraph of like facts and new knowledge that you would need to encode this. Yeah, maybe you have a better understanding. Yeah.
Yeah, I think I see what you mean. So basically, maybe let's specifically talk about embedding models, right? Whether you want to do zero shot or you want to do fine tune or continue fine tuning, you have three options actually. Zero shot means you just take the off the shelf one. Fine tuning means that you fine tune on the LangChain documentation, maybe on January 2024, and you don't do anything else after for 2 years, right? Continue fine tuning means that you keep fine tuning on LangChain new documentations probably every day, every 2 days, right? So I think this depends on how fast your world is changing, like how fast your corpus is changing to some degree, right? So I think for LangChain documentation, because LangChain, the documentation is so new, right? Many of the lingos are very new, and even not only the lingos, right? Also, for example, like even the logic, right? The deep scientific concept about all of this, RAG and agent chain, so on and so forth, are new. So you probably have to fine tune a little bit to get the best performance. However, once you fine tune once, you're already familiar with this kind of like way of thinking about that. Basically, it's kind of like, suppose you are a human retriever. Suppose you are you are doing this retrieve yourself, right? So you read, you systematically study LangChain once. You try to understand what LangChain is really about, and that's kind of the fine tuning step for yourself, right? And and once you do this, you probably don't have to systematically study LangChain again to retrieve further documents, right? Even LangChain's doc got updated, right? Maybe every month, and LangChain's documentation got updated a little bit. You don't have to systematically retrain yourself to be able to retrieve new documents from LangChain. And that's the beauty of the retrieval model, right? Like even the corpus got changed, you don't necessarily have to change your retrieval method. But maybe at some point, LangChain pivot. I'm not saying that they should pivot or anything, right? I'm just using it as an example. But suppose LangChain pivot to a completely different company, right? And then every concept is changing. And then you probably have to restudy the whole documentation corpus. And that's kind of like a continual fine tuning, or maybe a second fine tuning phase, right? So I think it just really depends on how fast the world is changing. If the world is changing really fast, you probably have to continue to fine tune. If the world is changing very, very slowly, you don't necessarily even have to fine tune at all. You can just do zero shot embedding models.
Yeah, it's so exciting. I'm sure a lot of like Weaviate people building with Weaviate, hearing about who have their code documentation, is certainly something I've seen that's very popular. Are excited to hear about this. Things like you don't need too much data, too much documentation to take advantage of this, and all that is so exciting. Maybe if we could quickly touch on that problem of re-embedding the data set, because if you continually train, then you got to re-embed the data set. Do you see that as a big problem for continual fine tuning of embeddings?
Yeah, so I think right now, if you fine tune the embedding models, at least using our technology or using any technologies available here, I don't think actually any other companies provide fine tuning other than Voyage. So but if you fine tune, you have to re-embed the whole corpus. So we are not super concerned about this just because economically, because anyway you have to fine tune on a new corpus that already costs something. It's not very expensive if you don't have a lot of documents, but that costs maybe X dollars. And um, and the cost of re-embedding, re-indexing the whole corpus probably is less than X. It's probably X over 2, X over 5, something like that. So that's why we are not very concerned about re-embedding the whole corpus if you have already fine-tuned. In the future, everything will be much cheaper, right? Fine-tuning will be on the fly. You don't have to fine-tune on everything again. You have to only fine-tune on the differences of the corpus. And when you update your embedding your embeddings, not the embedding models. When you update your embeddings, you can also only update embeddings, maybe some part of the embeddings, maybe only update 10 coordinates of the embeddings, so that you can keep the cost even lower. But that's for future developments.
Oh, that, yeah, so exciting. I love the thinking behind that. So kind of one other anchoring question I wanted to ask you, and if this is kind of like a secret sauce question, then feel free, of course, to pass it. But I'm really curious about serving an embeddings API, building products around like model inference APIs. Like kind of what goes under the hood. You have like how is like kind of like concurrency with GPUs, batching, all that kind of good stuff.
Yeah. I think that's a great question. Actually, this is also something we are trying to figure out. So because the reason here is that um, serving an API for many users, especially when you have embedding users using the embedding models, is kind of a little bit different from just serving the models for one user. And the reason is that some users probably embed. We have seen this, right? Some users embed 10 billion tokens a day, right? Because we give them some higher token per minute TPM or request per minute constraints, and they embed 10 billion tokens a day. And some users are doing 10 million tokens every day. So there's such a heterogeneity in terms of how people are using embedding models, because some people are using it for the queries in production, and some people are only embedding their initial corpus, and so on and so forth, right? So that gave us a lot of new questions in some sense, because we have to restrict the TPM and RPM for every different users in some different ways, and we have to deal with the backend, make it very reliable. What if you have a spike, right? And for example, one thing, this is not necessarily a secret source because it's kind of easy to think about, but probably hard to implement, is that it's not exactly very hard to implement either. So one thing could be that you can kind of automatically detect whether the users are sensitive to the latency, and then see what's the best way to optimize the trade-off between latency and throughput. So I think this probably also depends a little bit on, for example, whether they're embedding a batch, right? So I think you also probably mentioned before that sometimes you have to have a batch transformation for these embedding models. So, and our view is that we should just make users as easy as possible. So batch transformation, that's a very good idea, but it's not 100% necessary for the users to understand the differences between batch transformation and the other embedding APIs. Because if you have a very big batch, you have a 10 billion token corpus. Ideally we want the users to be able to just keep sending us all the tokens, and we do it ourselves on our side, right? So if you have like a 100 billion tokens, just keep sending it to us, right? And as fast as we can, and we will do whatever we can do on the back end. Maybe we gradually send back all the vectors to you, or maybe we wait a little bit, probably for 2 hours, and send back the embeddings to you. So, but that means that on the back end we have to be clever, right? We have to know whether you are sensitive to the latency. If you send us suppose you send us one request with only one sentence, then very naturally you are very sensitive to latency. Maybe you are using this in production. You have to see the result in 100 milliseconds. But if you keep sending us, right? If you send us or you've sent us a large batch, this large batch already have maybe 1 million tokens in a single batch. There's no chance you are expecting that we send it back in 100 milliseconds. Probably you care more about the throughput. And then we are going to do something on the back end to optimize for the throughput instead of the latency. We still keep the latency the same as if you are sending it normally, but we can optimize something else. We can do some other things. For example, one thing we can do is that we can use cheaper GPUs and more GPUs to maximize the throughput and still keep the latency when you have a large batch. But this technique wouldn't work if you have only one example. If you have only one example, it's all about how fast the GPUs can run, right? But if you have 100 examples, we can parallelize it across multiple cheaper GPUs. So there are a lot of these kind of small low-level optimizations we have to do on the system side. I don't think these are kind of really secret sauce, and they are not rocket science either. But they are a little bit special to embedding model APIs.
I love that. I think that's so interesting. I think hopefully we have a lot of systems people listening to the podcast. I hope. And one of the podcasts I really liked was with Rohit Agarwal from Portkey, where they have kind of like a load balancer between different LLM APIs. And a big thing with Weaviate is like hot storage and cold cloud storage. And I think kind of coming back to the DSPy thing, I'm super interested in kind of like stateful chains and what kind of like in-memory data structures when you want to use disk and all this. There's like so much to this kind of like routing of data and all that. Tengyu, this has been such an exciting podcast. I've learned so much from this conversation. I really want to ask you this sort of big anchoring question of, there's already been so many topics in the air through this podcast, but just kind of like, what inspires you the most? What's getting you out of bed in the morning, just with AI and directions for the future?
Yeah, so I think it depends on what's the horizon you are talking about, right? So if it's like 2 weeks, I'm very excited about our legal embedding model we are gonna launch in 2 to 3 weeks. If you are talking about 6 months, I'm very excited about a sequence of embedding models we can do. For the long run, I think the one of the exciting thing we have, in my opinion, about AI these days is that it becomes kind of like a little more modularized to some degree than before. So 5, 10 years ago, if you use AI for a particular use case, you have to collect data, you have to fine tune your model, you have to choose your architecture, you have to do everything from scratch to some extent. But now, at least you have a very, very strong baseline, which is that you just connect existing off-the-shelf component. So in some sense, using AI becomes much easier than using machine learning 5, 10 years ago, right? You need to know much less details, right? So in some sense, we got like the model providers, right? Like Voyage, we got all the messy, dirty work done for you for training the embedding models, and then this model just is very powerful, and you don't need to know how the models are trained, and just have to use the output, right? So, but before, when you use machine learning model, you have to understand a lot of things, right? So from all the way from data collection to how to fine tune how to train the model. So I think that's one of the amazing thing about AI these days. It kind of lower the bar for people to use AI, and maybe makes it harder to build AI components. I don't know, but that seems to be the trade-off.
Yeah, amazing. I was already so excited about our Voyage integration with Weaviate kind of going into the podcast, but now sort of picking your brain more. I think this is just so exciting. These kind of the continued advancement of embedding models and performance and the way it complements with these vector indexes and vector databases is all just such an exciting time to be working in RAG and this kind of we even like generative feedback loops is like our phrase of kind of going beyond RAG and beyond chatbots and just these like horribly complex LM programs that manage to, but too much going on with that. But anyways, thank you so much for joining the podcast. It's been so cool to meet you and learn about how you see these things.
Yeah, thanks so much for having me. Yeah, this is great. Thanks.